everybody. Thanks a lot for the invitation to talk here to Konstantin and Volker and Sebastian and MS1P in general. So we are not developing, or we are not contributing to the development of FHI-aims, but we are heavy users in many respects. And so in this presentation, I would like to talk you on a journey into crystal structure prediction, and then you will see that we also do free energy calculations, which are actually not unlike what Volker has described. And I will show you how this performs in the realm of organic material and how we actually got to trusted error bars. And this is all what we call the trust method. So in this presentation, I have a short introduction. Then I will present Avant-Garde Materials Simulation, so who we are as a company. I will take you into our universe of molecules, crystals, and drug products. I will then describe what we understand by modern crystal structure prediction and what has recently changed. Then I will talk in more length about our free energy calculations with the trust method and how this performs on predicting phase transitions as a function of temperature and relative humidity. And in the end, I will conclude. So Avant-Garde Materials Simulation. So we are a privately owned business. We're actually a family business. We are located in the south of Germany, in Freiburg. Originally, the company was born in France. Actually, we still have a French mother company. Freiburg is not only well known for crystal structure prediction, it's probably even better known for the fact that it is the big city of the Black Forest. So it's quite a nice area in terms of as far as the mountains are concerned. It's also well known for its two sustainable districts, and one of them, Vauban, is where we actually more or less live and work. So our office is very close to the kind of thing you see at the left. So houses that do not heating, people who do not own cars, rainwater that is infiltrated back into the ground, that kind of thing. So Freiburg is definitely worth a visit. As far as we are concerned, we are a family business, so we have been developing software for crystal structure prediction since 2002. Now, I think that already will tell you that it's a hell of a problem. So when I started in 2002, I believed, give me 3 years, and then I do something else with my life. And now, 22 years later, I'm still promoting crystal structure prediction. And well, until very recently, the company has had 13 people, of which 8 held a PhD from 8 nationalities in total. We have actually just hired 2 more software developers. And in terms of our value set, we clearly have the value set of a family business. So one of our specificities is that we do not take venture capital because we are very attached to our freedom. Then I always make a joke when I talk to an international audience that it's hard to get everybody in a team on a team photo because people simply have too much vacation in Germany. So in case you're looking for a job, and I will come back to that, Germany is actually a cool place to work. Now, as a company, we develop software, and our main product is called GRACE. GRACE stands for the Generation Ranking and Characterization Engine. And even though we have one main product, we have essentially 2 business models. So either we do contract research with our software, or we sell the software, both to large pharmaceutical companies, mainly because that's where the main application for crystal structure prediction is. We have a couple of unique modules. We have a force field factory, which automatically generates force fields fitted to ab initio data from scratch, also for third-party applications. We have a CSP factory that does the actual crystal structure prediction study. We have a structure solution factory that does crystal structure prediction solutions. And all our software has been written for high-performance computing setups, so originally Linux clusters running a resource management system. And since various clouds have also started to look like Linux clusters, GRACE is also running on the cloud. Now, what do we do with our software? So our work is mainly about molecules, crystals, and drug products. And so if I say the same thing in pictures, then what we deal with are molecules. For those molecules, we try to determine the unit cells of the experimental structures or predicted structures that may become experimental structures. A little bit broader, we are also interested in crystal packings and maybe in morphology or that kind of thing. And then the universe of our users and customers, that is more the real world, so crystallites, crystalline powders, and drug products. And where we meet with them is at the interface. So it's the interface between the outcome of a prediction and reality. Now, one of the fun things about organic crystals is that there's polymorphism. Of course, we also have polymorphism for inorganic compounds, but polymorphism turns out to be particularly important for the pharmaceuticals industry. And the fact is that a given molecule, paracetamol, for instance, can form different crystal packings. So here, the two more stable polymorphs are shown, but since those structures were published, actually many more polymorphs of paracetamol have been discovered. I think today we are at something between 7 and 9. And so the different crystal structures, the different polymorphs, they can have very different properties in terms of solubility, dissolution rate, density, morphology. And so the pharmaceutical companies, they have to be very careful always to bring the same polymorph to the market. And that is not easy. And it is not easy because, first of all, there is a phenomenon called late appearing crystal forms. So the example I show here is actually on work done in the 90s, and this was work done at Sanofi, and this is somewhat related to the origin of our own company, because after this had happened to a person at Sanofi called Marc-Antoine Perrin, he actually really wanted to have software for this kind of problem, and he was then the first person who gave me a contract. So I and the company, we owe everything to a person called Marc-Antoine Perrin, who is now retired. And so what happened here was that they had a compound under development, so to cure a disease. I do not remember which disease it was. And over a period of 5 years, they more or less accidentally discovered 3 forms. And each time they discovered a new form, they had to change things in the formulations. The formulation is what you administer to a patient. And then after the 3rd form, they said, okay, enough is enough. Now we do heavy experimental screening, and then there will be no more forms. And they screened, no new form was found in the screening. And then accidentally again, a form 4 occurred in 1996. And if you look at the phase diagrams, and this form 4 is actually is a relevant form at room temperature, so at ambient conditions. And so it happens quite often to pharmaceuticals companies that the really important form is discovered accidentally and very late in the product development cycle. And if that happens, things can actually turn really bad, and that is due to a phenomenon called disappearing polymorphs. So it can happen that a late appearing form occurs. That is the most stable form thermodynamically. It is actually much less soluble because much more stable than all the forms you had before. Now you have polluted your entire production site or your lab with a new form, and then you can't make the old forms anymore. So even if you want it, you cannot go back to the formulation which you previously administered to patients. And of course, if that happens, then you cannot sell the drug anymore, and then that can inflict very heavy financial losses. And that happened for a couple of compounds in human history, but the one or two of the extremes are ritonavir and rotigotine. So it's estimated that Abbott, over the ritonavir case, lost something like a couple of $100 million. And so what is a disappearing polymorph? So disappearing polymorphs are crystal forms that are first observed experimentally, but later become difficult or impossible to obtain because of a late appearing, more stable crystal form. And it is really this disappearing polymorph problem that provided the funding to develop modern approaches for crystal structure prediction for almost 22 years, just because it is such an important problem that can become massively expensive if a polymorph accident happens. Now, what has modern crystal structure prediction to offer to alleviate this disappearing polymorph risk? The main object that we calculate is what is called a crystal energy landscape. And here you see such a crystal energy landscape for a compound that is shown. So on this crystal energy landscape, every full symbol is a predicted crystal structure. And then these crystal structures with their energies are shown versus density on the x-axis and versus energy on the y-axis. The density is not a very important property, it's just used to spread out the points. Now, crystal energy landscapes have been calculated for a long time by many people. Now, what makes this a modern crystal energy landscape? First of all, if you look at the landscapes, then every predicted energy carries an error bar. And so today we know to which extent we can trust the free energy calculations, and then that of course makes it possible to take decisions based on risk analysis in the production process. You will also see that there are different colors, and the different colors relate to different hydration states. So here we compare anhydrates, monohydrates, and dihydrates. And if we are able to do this comparison, then somehow we have to bring relative humidity into the equation. So all these relative stabilities have actually been calculated as a function of temperature and relative humidity. And the method that allows us to do those predictions with the error bars and to calculate the phase transitions as a function of temperature and relative humidity, that is called TRUST. TRUST stands for temperature and relative humidity dependent free energy calculations with standard deviations. And we had the pleasure to get this published in Nature last year, also because of the very extensive validation that has been done and that gave us the error bars. Before I say more about the TRUST method, I have to say a couple of words about our daily bread and butter. So the kind of thing we do here, our contract research department, you see here, our contract research department does this something like 50 times per year. And then we have large pharmaceutical companies as software customers who do this per company something like 50 times per year. And so what is the game that is played? The user, can be an internal user for a pharmaceutical company, comes with a compound, with a chemical drawing of the compound. From there, the crystal energy landscape is calculated. Often they're experimental forms, but their structures may not have been solved. But if they crystallize, then a powder pattern can readily be measured. And so it's easy to compare the predicted crystal structures against experimental powder patterns. For the case here, rotigotine, which is one of the disappearing polymorph accidents, today we would readily realize that, that the experimental powder diffraction pattern actually corresponds to the blue open circle, so it's called form number 1 for the pharma customer. And we would also see that there's actually a much more stable form out there, here represented by the red circle, that has not yet been discovered. We would be able to put a solubility difference on the difference between the two polymorphs, and we would say, okay, the missing form is 8 times less soluble. The customer would then say, oh, this is very, very dangerous. And then together with the customer, we would enter into a risk reduction strategy, either to make or to avoid that form. And in pharmaceutical companies, that triggers real decisions. So, for instance, if they have a case like this one, where a landscape has been built and an experimental form has been placed on the landscape, and according to the error bar, the most stable predicted structure is truly still missing and is truly more stable. I have to say all our error bars are 1 sigma error bars, so we are not at the error bars of the engineers yet, which are often 3, 4, 5 sigma error bars. Then pharmaceutical companies will act on this. And they have a variety of ways how they can act on this. So they can simply intensify their standard experimental screening, or because we now know the crystal structure of the form that should be observed but has not yet been observed, we can try a rational crystallization experiment design to make that very form. Or since, as you will see, we have a certain control over the phase diagrams, we can try to go to thermodynamic variables like temperature, pressure, or relative humidity. That makes it more likely to observe the form. If all that fails, then actually the behavior becomes more defensive and it is about avoiding the new form. So then in production, pharmaceutical companies would go to thermodynamic variables that make it less likely to observe the missing form. When the chemistry is not 100% nailed down, for instance, when pharmaceutical companies work with co-crystals or with salts, where there's a certain leeway on the co-former, on the counter ion, there's actually also another option, and the other option is to try to change the co-former and the counter ion to get to another onto another landscape for different chemical species, different chemical compound, and that landscape then would not exhibit disappearing polymorph risk. And in the very end, if nothing can be done about it, at least companies can prepare for a potential disappearing polymorph event. And one option could be, for instance, that they simply have more crystalline material on stock should their crystallization process ever break. So real decisions are based on these predictions every day. Now let me come back quite extensively to our free energy calculations and say, so for us, in the way how we use crystal structure predictions has really been a before and an after trust. Everything has become extremely straightforward since we have trust. Before I say more about the trust method, I have to say that this has done with a lot of help from other people. To start with, of course, our starting point for what we do today was what we learned from Alexander and his I think, PhD student. It was Johannes Heuer. And so we took their method and then we added certain things to their method, and that gave us trust. But their method was really our starting point. And then to validate this method extensionally, we needed a lot of data, and that data was very hard to find, and the literature was not enough. So we had a lot of pharmaceutical companies who actually contributed data to our validation of the trust method. Let me first tell you what the trust method is. So we call this trust method a composite method. A composite means that it actually consists of many different calculations, which all have to be acted out together to compensate for each other's shortcomings, so that in the end you get something relatively accurate. And if I quickly talk you through, so like in the original method, we optimize crystal structures with relatively inexpensive ab initio. Then, and here I'm in the left branch, then we optimize, then we do single point corrections on those optimized structures for certain effects. For instance, light to tight basis hit, PBE to PBE0 functional, our own van der Waals to the MBD van der Waals. And so we do single point corrections on the crystal structures. But very often, and especially for certain molecules, there's a problem with electron delocalization error. And so we also do single point monomer corrections for the molecules in the crystal structure. And this is what I would, so referring to the literature, this is what I would call Barron's method. So I think Barron was, and his group, they were the first ones to show that this is really useful on a compound called Roy. And then in the vibrational branch, of course, we also do supercell phonon calculations. So we sample the Hessian matrix by atomic displacements, construct the dynamic matrix, solve for the phonons. And that can be done in principle with FHI-aims for relatively large supercells, but that would be way too costly, because please keep in mind our methods, they have to work for, depending on where you are in the crystal structure prediction funnel, for billions, millions, thousands, or at least hundreds of crystal structures. And so whenever we do a CSP, we need free energies for 100 crystal structures and not only for one. And so what we do has to be inexpensive just as well as accurate. And so for these ab initio supercell calculations, we do various corrections. If we have imaginary modes, then we do go for the explicit, so we explicitly sample the one-dimensional potential, and then we solve the one-dimensional Schrödinger equation to at least get some sort of correction for the anhomogeneity of those modes. To get the phonon dispersion right, we do a very large cell phonon dispersion correction at force field level, and then we also correct a couple of other things that have proven to be less important. One important point here, and I'll come back to FHI-aims, is that everything is a QM calculation is actually carried out with FHI-aims, so Grace has a driver for FHI-aims. We can also do those calculations in the gas phase. Gas phase calculations are easier because there is no environment, and the only thing I have to add here is that we use a rigid rotor harmonic oscillator approximation. And again, the gas phase calculations are done with FHI-aims. Here it really comes in handy that both the solid state and the gas phase can be handled with the same tool. So I have to say a couple of words on how we calculate multi-stoichiometry landscapes. So landscapes, how do we compare hydrates to anhydrates? And here it's important to realize that every phase transition between two crystals, so anhydrate-anhydrate or anhydrate-hydrate, is actually a measurement of a free energy, because by definition, at the phase transition, the free energy difference is 0. And what this means is that if we, for instance, compare an anhydrate to a monohydrate, and so for that case, N on this slide would be equal to 1, then the free energy of the anhydrate plus the free energy of one water molecule in the gas phase must be equal to the free energy of the monohydrate, always normalized to one molecule. So that's how we calculate phase transitions. And then to compare multiple stoichiometries, it's more convenient to put the gas phase term onto the right side. So we actually subtract the gas phase free energy from the hydrate free energy. And then we can compare every hydrate to the anhydrate, so we can also compare the hydrates among themselves. And in these plots, so these crystal energy landscapes with error bars for different hydration states that I will show you, so things which have the same energy, so the same location on the y-axis, are structures of equal free energy with a phase transition condition. Before I continue in our universe, I have to say that all this would probably not be possible without FHI-aims, because FHI-aims for these free energy calculations really brings a lot of features that are really important. So it has a very small basis set superpositioning error. It has very affordable hybrid DFT. It has a very good many-body dispersion implementation. It scales linearly with system size, and it has a very high numerical accuracy on the forces. And all this is required for the kind of work that we do with trust. So for the moment, I have only talked about trust as an energy calculation method, but trust is also a free energy benchmark. So we have done a lot of work with our academic partners and also with our pharmaceutical customers to get our hands on reliable free energy differences for industrially relevant compounds. And in total, we have collected 37 free energy pairs. 12 of them come from solubility ratios. So two polymorphs, if you measure their solubility in a solvent where they are poorly soluble, so you are almost in infinite dilution, then the solubility ratio is actually related to the free energy difference between the two forms. Then we have two anhydrate-anhydrate phase transitions as a function of temperature, and we have 21 hydrate-anhydrate phase transitions as a function of relative humidity. Now you may wonder, why is there so little data? Well, the reason is that a lot of conditions need to be fulfilled. The crystal structures of all experimental forms must have been solved. There should not be massive disorder, because otherwise the entire problem becomes more complicated. And then the phase transition has to be characterized, so there needs to be a thermodynamic variable before and after the phase transition, and the phase transition has to be reversible. And so if you look at the literature, there's hardly, so there are data sets, but they're hardly ever complete. Even if they are complete, they may not fulfill all quality criteria. So we in total have 37 free energy differences, but there are only 25 we really trust. So whenever we extract numbers, then those numbers are only against 25. So trust is also an experimental free energy benchmark. And then trust is also an error estimation model, because of course, so pharmaceutical companies, they have to base decisions on our predictions. And so for them, it's not important to know how well our calculations perform on the benchmark. For them, it's important to know how well our calculations perform for their molecule, which is not part of the benchmark. So we need an error estimation model. And as you will see, our error estimation model is relatively simple, but considering the little amount of data we have to calibrate it, we couldn't make it more complicated. Our basic assumption is that there's a sort of energy error per atom. And we assume that every atom in a crystal, every atom in the asymmetric unit sees a somewhat different environment. And then over those different environments, there is error propagation for the error per atom. And we assume that error propagation is Gaussian. So we can use Gaussian error statistics to propagate our error, for instance, to the asymmetric unit of a crystal or to an energy difference between two crystal structures. And we only distinguish two atomic errors for water atoms and for all other atoms. And those two atomic errors, we have fitted them to the experimental free energy differences in our predictions. Now, you are probably not used to look at energy errors per atom, so I won't show you the numbers that we got out of the fit. The only thing I show you is this table. And if you want to retain only one number, then that is a 1.6. So at the moment, for a 60-atom compound with one chemical unit per asymmetric unit, so Z prime 1, and a monohydrate, we have an accuracy of 1.6 kilojoule per mole, measured against experiment, 1.6 kilojoule per mole. It has to be said that this is a sort of upper error for the prediction, for the calculation, because this is a combined experimental and computational error. And sometimes some of the data is not very accurate. For instance, for hydrate-anhydrate phase transitions in the data, there is a lot of hysteresis. So you do not always know at which relative humidity the phase transition actually takes place exactly. Good. I've said we assume Gaussian error propagation, and of course that somehow has to be justified. And so what has happened here is that we took all the experimental free energy differences. We calculated our computed free energy differences. We can subtract the two. So this is actually then a difference of differences of free energies. For that calculation, we can predict an error based on our error estimation model. We can divide the observed error through by the expected error. And if this has Gaussian behavior, then we expect to see a distribution which is a Gauss distribution around 0 with a width of 1. That is a blue curve. And if you compare the histogram that we get on our data to the blue curves, then you will realize that within our statistics, so we only have 25 cases we really trust, this actually pretty well follows Gaussian error propagation. So at least our assumption of Gaussian error propagation is reasonable. And our compounds actually also cover the decent size range. There's one thing I haven't told you yet, and that is that we also fit an offset for water, but it's not as bad as it may seem. And so please first look at the plot to the right only, and that is a plot where no specific offset has been fitted. And what this plot shows you is a comparison of the predicted and the experimental relative humidities for the phase transitions. And if we would make perfect predictions, then every point would lie on the dashed diagonal. But as you can see, all the predictions are more or less under the dashed diagonal. So we are completely off to one side. And that is because there is a small error on the free energy difference between water in the gas phase and water in the solid state. And the practical way to solve this easily is that you fit in a free energy offset for water. And once you have that, then you get the plot to the right. Still, this method, we expect it to work for all solvent systems. And I have to show you two numbers there. So please, in the table, look only at the bottom numbers. So we first look at the green number. This green number that is related to relative humidity prediction with the offset. And so over all those relative humidity predictions, we get the prediction of the phase transition relative humidity right to within a factor of 1.7. So this is not 1.7% of relative humidity, this is a factor of 1.7. That means that if we predict a phase transition at 10% relative humidity, it may be, so the 1 sigma interval is from somewhere 7 to 17%. If you don't have the offset, then we still get phase transitions right to within a factor of 2.4, which is actually not much worse, but it's a little bit worse. So when we do pharma work, we use the offset.
Hey, Markus, you have around 3 minutes, if that's okay.
Thank you. I will be almost in time. So a couple of application examples. So we can, this is a landscape I already showed you. Now I show this again, and I want to take you from here to temperature dependence. And then I first have to show you what we cannot show. So we cannot simply plot the free energy as a function of temperature, because then we would get this, and then you don't see the differences. So what we typically do is we renormalize everything so that if we calculate, let's say, 10 free energies, then we set the average free energy to 0 over the full temperature range. And then we get plots like this. So now every colored line here for that compound is an experimentally observed forms. The colored lines cross, that's the predicted phase transition temperature. The error bars have now turned into stripes. The stripes have a diamond-shaped crossing region, and the 1 sigma interval of the prediction of the phase transition is somewhat related to the diamond shape. You also see the experimental phase transition temperature, 343 Kelvin, which actually falls into the 1 sigma interval of the prediction of the phase transition. But there's a big but, so the error on the phase transition is still something like a couple of hundred Kelvin. That is a lot. Experimentalists easily measure phase transition temperatures to within a Kelvin. And that means that to get to experimental accuracy, our energy calculations have to become a factor of 100 better. So be my guest, feel invited to try and to improve the method. The data is there. You can test that you are doing better. The same things can be done as a function of relative humidity. So here again, a crystal energy landscape. And by the way, I forgot to say about the previous landscape as well. So the experimental forms are also flagged here, and they're always at the bottom of those landscapes, or very often. That says also something about the accuracy of the method. And so here we use this example to show free energy dependence as a function of relative humidity. That is this plot. So again, the error bars have now turned into bands. We can express a 1 sigma error interval for the expected phase transition. Here the phase transition is between an anhydrate and a hemihydrate, and that phase transition is truly observed. It is observed at 14% relative humidity. So this is within the 1 sigma error interval. And for the relative humidities, actually our predictability gets into the range of the experimental values because, as I said before, often there's a lot of hysteresis. So here we are actually not that much off from the kind of accuracies experimentalists get. We can also do solid-solid phase diagrams, so stability regions as a function of temperature and relative humidity. Here again, for the hemihydrate-anhydrate case, so the dashed line would be the predicted coexistence curve, and the shaded regions around it, that would be the 1 sigma error interval. And the stars, those are the experimentally observed coexistence conditions. Conclusion. So first of all, there is a method which offers temperature and relative humidity dependent free energy calculations with standard deviations. The acronym is TRUST, and this is heavily based on calculations with FHI-aims. Predictions, the accuracy of predictions still has to be taken with a grain of salt. So TRUST predicts if to expect phase transitions between predicted and or experimental crystal structures, but not where exactly to expect a phase transition. Then TRUST is a composite energy calculation method, is all at once composite energy calculation method, a benchmark and an error estimation model. And our current accuracy is in the range of 1.6 kilojoule per mole for a 60 atom monohydrate. Thank you very much for your attention. My last slide, we are heavily recruiting. So should you be looking for a job in science, IT or administration, please visit our website. We have a lot of interesting open positions. Thank you very much.
Thank you, Markus, also for the nice talk. Yeah, also some claps from the audience, so they also enjoyed the talk. So I will post, before we come to the Q&A, I will quickly post the links to both the short YouTube video as well as the Slack invite for tomorrow. But I will now give over again to James, who will lead the Q&A also for the second part.
Yeah, thanks, Konstantin. Thanks, Markus, for the really nice talk. So yeah, we already have one question in the chat, in the Q&A chat. So you mentioned that the experimental powder X-ray diffraction can be easily matched to the crystal structures of the CSP landscape. Could you expand on how you do this?
Yeah, so this originally started from an idea developed by Martin Ulrich Schmid's group. I think the person was Stefan Habermehl in Frankfurt. But so, of course, there are tricky bits. Yeah? So the predicted unit cells do not exactly match the experimental unit cells. There may be temperature effects that are not captured, so the diffraction peaks do not overlap. There may be strong preferred orientation that may kill a whole cone in the reciprocal space. And so this is not straightforward, but we are software developers, so we have a crystal structure prediction funnel, we have a powder pattern matching funnel, and that will first do cheap cross-correlation, then expensive cross-correlation, and then in the end, full Rietveld refinement, all fully automatically. And so for us, it's easy to match. And for our users, it's easy to match. It is not easy to match in general.
Thanks, Marcus. So I've got a hand raised as well from Eugene, so I'll just allow you to talk.
You hear me?
Yes.
Yeah.
I would have at least one question, perhaps two if time allows. First one is, you said like the accuracy of your free energy is around 1.6 kilojoule per mole, you said?
Yes.
Can you then explain where this more sizable, for example, temperature standard deviation comes from? Like what would you think is the source of error you're still forgetting? Or is this just because you have too little statistics due to the small benchmark set?
No, so first of all, where does a strong error on the temperature come from, phase transition temperature come from? Well, the problem is that the free energy curves, they're all very similar. And so it is a tiny slope difference combined with the error of the free energy prediction, which ultimately gives you the free energy on the phase transition prediction. Mm-hmm. And so our problem is that we are comparing things which are just horribly similar. Yeah. Most of the free energy is actually sort of molecular effect and not a crystal effect, because all the crystal packings, they have very similar temperature evolution. Mm-hmm. So what really is the problem is the similarity of the slopes, not so much the accuracy of the predictions. But then, of course, there is an issue with the accuracy of the predictions. So, for instance, what is completely neglected at the moment is thermal lattice expansion. And so my gut feeling would be that thermal lattice expansion is maybe the next big effect that limits us. But we would have to calculate it not for 1, 2, or 10 compounds per year, structures per year. We would have to calculate it for thousands or tens of thousands of structures per year. So we as a service provider to the pharmaceuticals industry, we will only do things which are ultimately also economically reasonable. So since there are a couple of obvious things to bring this to higher accuracy, one of them is thermal lattice expansion. Another one would be higher level of theory for all functionals, higher level of theory also for the monomer corrections. But then it would very rapidly be completely uneconomical and maybe even too uneconomical to do everything on the benchmark. So even comparing to the benchmark will become very expensive.
But then have you, for example, talking about the electronic correlation you mentioned, because that's what I am working on as well. Because you use an MP2 correction, have you, for example, considered collaborating with Frank Nese with their local couple cluster methods, where they usually do very huge molecules with very reliable accuracy?
We are very happy for everybody who wants to try other things to improve this. So we can easily provide the molecular structures, for instance, so that people can try higher level methods. Right. We also already collaborate with a couple of people to make this better, and we are running our own tests. But so this is completely open. Yeah. So we learned a lot here originally from Alexander and Johannes. Right. And if it then goes back to other people who further improve the method, maybe with or without our help, that's perfectly fine for us. And so if you want to send me a link or put me into contact, I'm happy about everything.
Okay, nice. Do I have time for one more question, or is someone else raising their hand already?
Yeah, go ahead.
Can I? It's more to the beginning of your presentation where you mentioned the disappearing polymorphs. Perhaps I'm confused, but I didn't understand, where does this disappearance come from? Is it because the polymorphs are so similar in energy that they slowly transform one to another, or what is the reason that the one polymorph disappears at some point?
So when it happens, the effect is massive. I tell you the anecdote. When Form 2 suddenly occurred for ritonavir, and they couldn't make Form 1 anymore, they still had the sites that produced in Italy, and they sent scientists over to Italy. Right. Then as soon as the people appeared there, a day later, they couldn't make reliable from 1 anymore. And you are right, it doesn't necessarily mean that from 1 doesn't crystallize at all anymore. For the pharma companies, it's bad enough that from 1 is always mixed with a certain amount of from 2, and so don't control the system anymore. We ourselves, we have once forecasted a disappearing amorphous phase case. So the companies, they couldn't crystallize. A company could only make an amorphous phase. We made a prediction, and the prediction made everybody believe that one day it would crystallize. And the day they had really crystallized, they lost within a day they lost the amorphous form in the entire building, and they couldn't make the amorphous form anymore. And they still had a little bit of amorphous material in a glass capillary, and they behaved like before. So this is not something strange like a morphic field that traverses the universe because something has been crystallized for the first time. Yeah? So it's not esoterical, it's about seeds, and the glass capillary kept out the seeds.
Yeah, crystallization is always very difficult.
Yeah.
Okay, I start to understand. It seemed very mystical to me when you explained it first time. Now it makes more sense. Okay, thanks a lot.
Questions? So we have one in the chat from Kyle. So firstly, thanks you for the talk. And then he asked, he saw in your trust workflow that you use PBE with the NP dispersion correction. So what are the advantages to using the NP method, and is it available in FHI-aims?
So it's not available. So first of all, we have published our parameters. Yeah. So there's a 2005 paper. So NP stands for Neumann Perrin. The academics completely forgot that we had the first empirical van der Waals correction in 2005, but that's live. Yeah. It actually turned out that it's more accurate on the geometries than MBD. And for the simple reason that it is fitted to real crystal structures and not to gas phase dimer information. So since we have somewhat better accuracy on the crystal unit cells, we prefer to pre-optimize with our own method.
Okay. And yeah, so it's not available also in FHI-aims yet, but parameters are there and the literature's there. Okay, so I have a question also in the chat from Cameron Nickerson. So what is the upper limit of atoms per unit cell that you can practically use your trust method for, and which part of the process is the limiting factor?
Which we can use the trust method for. I think the limit on the trust method is not massive, because as long as there's symmetry, since we do atomic displacements, we only do those for the atoms in the asymmetric unit. And if molecules become bigger, then we create less supercells, because maybe the cell is already big enough as a supercell. So I cannot honestly tell you, because in crystal structure prediction the limiting steps are actually somewhere else. So it's an actual crystal structure prediction that is hard to do for larger molecules. And so 100 atoms per molecule are a lot of atoms today. So ritonavir has roughly 100 atoms, and we can do this with 1 molecule per asymmetric unit, but not with 2 molecules per asymmetric unit. But the limiting step is not the trust. The limiting step is the overall crystal structure prediction funnel.
Thanks, Marcus. So I don't see any other questions open at the moment, or no other hands raised. So yeah, maybe I'll just hand back to Konstantin at this stage to wrap up the webinar.
Yeah, thank you, James, and thank you also to Marcus and once again to Volker. I think we're at